students, welcome to Nuclear Physics Lectures. I'm Dr. Pervez Ahmed. And this particular lectures, we will discuss about the standard models. So, what is the standard models? What is something special about these models, or what we have in this particular models? So let's answer the first questions. That is, what is it? I mean, whenever we heard the words or whenever we heard about the standard models, so the first questions that we have in mind is that what is it? I mean, this is the question that people are asking whenever they heard about the standard model. So they say, what is it? So the best answer for this is, I mean, it's the best theoretical framework we have for particle physics today. I mean, the standard models. It's what it is the best theoretical framework we have for the particle physics today. So what it means? It means that it has been a remarkable success, but we know that it's incomplete. I mean, it's a theoretical framework which helps us to understand the particle physics, that is the interaction of the particle inside the nucleus. And as a result of that interactions, the forces that we have, the fundamental forces and their behaviors, I mean, we are being able to understand. So, I mean, there are people, there are scientists who are talking about the standard models, and they say that it has been a remarkable success. But along with that, they're saying that we know that it's incomplete. I mean, this model, the standard model, it's still incomplete. So, what does the phrase standard models mean? I mean, if we are saying that it's standard models, and on one side, we're saying that it has remarkable success in explaining the behaviors of the particles and the forces which is being operational among the particles are the forces which go on, are the forces which act upon by the different forces. So, what actually it means? If we are saying that we are utilizing the phrase that it's a standard model, so what is mean by this standard models mean? So it means that unifications of all matters into two types of particles. So what are they? What it means? It means that a unification of the electromagnetic and weak nuclear force. Uh, so what it means? It means that a descriptions of the interactions between the fundamental particles in terms of the exchange of the fundamental force particles. So something it does not do. I mean, something the standard model is plain, and some things we are saying that just like we mentioned in this slide, it has remarkable success, but at the same time, we are saying that this particular model is incomplete. So, what is I mean, those things are due to which we are saying that this model is incomplete. So, let's deal with those. It means that uh, when we are saying that this model is incomplete, so it means that it does not unify the strong and electro-weak forces. I mean, this is the first. Incompatibility, or we can say that is the first drawback of the standard model, and it's that it does not unify the strong and electro-weak force. The second fact, which we are saying that the second drawback of the standard models is that it ignores gravity. I mean, there's nothing about the gravity in this particular model, so it does not tell us anything about how it might be unified with the other forces. I mean, it's this kind of models it does not talk about the gravity, so there is no particular framework that how gravity can be unified with other forces. So still in this reference, we can say that standard model is incomplete. So it does not explain why there are so many generation of the particle. You know that there are basically three generation of the particle, but according to this model, we don't have any such information which can explain that why there are so many generations of the particles. So along with that, it does not explain the disappearance of antimatters and the universe. I mean, this is the incompatibility. I mean, we can say is the incompatibility, or we can say that the incompleteness of the standard models, that it do not say, it doesn't explain the disappearance of antimaters in the universe. So when we are talking about the unification of the matters, so throughout the history, we know that there have been attempts for the unifications. So if you have knowledge of the basic science, so from that particular knowledge, you know that the first attempts for the unification is being made in the early era of the science, and that attempts, the scientist or the philosopher first try to make the unification among the four basic factors, the four basic things that we have in the universe. That is, they unified air, fire, water, and earth. So this is the first attempt for the unifications by the early people working in the field of science. Then we have some of the effort for the unification of the forces, which is being put in the I mean, it's like in standard models. I mean, people trying to unify the different interactions. I mean, we already discussed about them in the previous lecture, that how different interactions, how different phenomena, they are initially brought into they are being unified in some of the well-known categories, and finally I mean, standard models has been developed. But we already mentioned on the previous slide, the standard model is incomplete. So if the standard model is incomplete, so why there's a lot of work, I mean, the scientists yet need to be I mean, they yet need to be done for, I mean, the success of this particular model. So how our forces are transmitted? I mean, the people in the 19th centuries, they were trying to explain these facts, that how the force field was. They were just trying to explain the phenomena. They were just trying to explain I mean, how the forces they are being transmitted. So they basically proposed the force fields. What actually they proposed, they were saying that if we have two charges, that is capital Q, that we have one charge that is being represented by a ball in red color, and a small charge, that is a small charge with a blue ball. And we say that these two forces, they are interacting with each other, so they should have a field between them, and these particles, they will not directly interact with each other according to quantum mechanics, according to which we say that if particles, we have particles like electrical particle or charged particle, so these particles, they will not directly interact with each other, and we are saying that according to quantum mechanics, we say that each particles, charged particle, they have an electric field around it until a certain point. So when the particle, the charged particles, they are made to interact. So first of all, their field interact. I mean, so the electric field, they have the electric field. So when this bigger particle interact with this small particle, so first of all, the field, they will interact. I mean, the particle will not interact directly with each other. So that's why in the 19th century, the force field was proposed. I mean, the same concept is being expressed for the gravitational force, or for the field of gravity. That is, we have the field of gravity between the masses, between the different masses. That if we have a smaller mass and we have a bigger mass mean, we mean that just like the mass of the sun, and for smaller mass may mean that the mass of the earth. So if these two masses, they interact, so first of all, they will interact with the field. So that was being proposed in the 19th century, and the people still believe in that. I mean, in modern era, we still believe in that the particles, they first of all interact with the field. So how do the particle create the force? I mean, in modern physics or modern era, we are saying that if we have particles, so the particles, they not only generate the force, but they also create the I mean, the particle not only act upon by the force, but they also generate the force. They also create the force. I mean, something like you can see it here in this particular example, in this particular diagrams. We have a person who's through the bowling ball, and now you can see that when he's throwing the bowling ball, so as soon as he's throwing, so you know that he's being filled with force in upward directions, and downwards we have a person who's trying to catch the ball. Once he trying to catch the ball, so along with that he's been experiencing a force. I mean, if abuse occurs and the this particular direction that this has been indicated by uh, the arrow sign. So just like that, we have the electromagnetic force. You know that the electromagnetic force, we have the electrons. Once the electrons get the energy, so it's jumped from one particular levels to other particular levels. So it's moved, it's remained in that particular levels according to the basic physics or the Bohr theory. As long as remain in this particular floor at this particular level, so it do not emit or gain any energy, but it want to leave this particular level, so it's being de-excited, it's moved to another level, so it's emit that energy in the form of photon. And you know that that photon is being responsible for the force of the for the electromagnetic force. So this analogy is just like similar to the one that we have for through bowling ball. And through bowling balls, it's just like the similar just like the similar analogy we have for the gravitational force and the electromagnetic force. So back to the unification of the matters. Uh, if you just have a close look on what we have inside the universe, so you know that if we start from a bit bigger scales, just like from the virus, you know that the virus has a size as bigger as 10 raised to power minus 7 meters. If we reduce the size of the virus, to the nanoscale, that is 10 raised to the power minus 9 meter. So at this particular scale, we have molecules. If we further trying to smaller the molecule, so what do we get? We come to the atomic scale, that is we have atoms, and the atomic scale is 10 raised to the power minus 10 meters. So if again we are trying to make it smaller, we want to break the nucleus, and we further want to go at a smaller scale. So the smaller scale from the atomic scale is the nuclear scale, that is we come to the nucleus, and the nuclear scale is 10 raised to power minus 4 meters. But we remember the nucleus not the fundamental particle. Nucleus is still breakable, just like we studied about the nuclear fissions. So when we break the nucleus or we go inside the nucleus, so again we have further smaller size particles. Beyond this smaller scales, beyond the nuclear scales, we have the scales for the subatomic particles, that is for the protons and the neutrons, and which we have that this particular scale is that is the nuclear scale is 10 raised to power minus 16 meters. But this is not the here we do not have the full stop here. Even we can go beyond this particular scales, beyond the nuclear scales, and we can travel less than 10 raised to power minus 15 minus 18 meters. And this is the scales where we say that we can look inside the protons, or where we can say that we can look inside the neutrons. And when we look inside the neutrons, or we look inside the proton, so we see the fundamental particles of the matter, which we call the cores. So till date, we are saying that core is being considered as the indivisible particles of the matters, or we can call it as the fundamental particles of the matter. But nobody knows that what will happen in the near futures. So the scientists, they are regularly doing the experiment with the particle physics. So that's why we have put a sign here that whether we can go beyond at a smaller scale than the cores, or this is a full stop. So here we have a question mark. Here we do not have a full stop. If we had a full stop here, so it would mean that we cannot go beyond. This is the final destination. But since we have the question mark, it means that the people, they are still trying to do the discoveries in the particle physics. So maybe in the near future we will have something very much strange. Maybe it's possible that the people will claim that a quark is no more the fundamental particle of matter, just like we were previously claiming about the nucleus, or we were claiming about the protons or neutrons. But then the discovery of the quarks, I mean, the previously developed ideology has been negated with the fundamental particles, with the concept of the fundamental particles. So the fundamental particles of the natures, you know that these matter particles, it has spin 1 by 2, and the fundamental particle of the matters, we say that they are being classified as quarks and leptons. uh, we already have some discussion about the quarks, we already have discussion about the leptons, and we will have many more discussions about the quarks, their classifications, and also we will have a discussion about the lepton. But at this particular point, we are saying that quarks and the leptons, it's all been the part of the matters, and they all have the span 1 by 2, and the charges, just like you can see it here. So I mean, they are being classified, they've been different type of the leptons, they are being type of the quarks. So accordingly they also have their respective charges, and along with that they also have their respective antiparticles. We also have the force particle. I mean, the lepton and the quarks, leptons and quarks, they are being called as the matter particles. Why matter particle? Because they constitute matter, different type of matters, and all of these have lepton and quark. They have span 1 by 2. That's why we call that. We also call them fermions. So there are also some of the particles which we call force particles, and those force particles, they have integral span. I mean, they have a complete span that is 1 or 2 or 3 or 4 and so on. So the force particles, which we also call the boson. So what are they? So we already mentioned in some of the previous slides that the force particles are gluons, photons, weak boson, and gravitons. So these are basically the particles which we call the force particles, and they all have the integral spin, just like you can see it here. The spin of the gluon is 1, the photon spin is 1, weak boson 1, but the graviton, which yet has to be discovered, it has a spin, integral span equal to 2. Some force diagrams, you know that fermion diagrams. So the diagrams for the electromagnetic force, I mean, it can be like this, and this we can also explain in the some of the coming lectures. The strong force, or the diagram for the strong nuclear force, that which is being operational between the protons or the neutrons, will look like this. That is, you know that, I mean, it's been the combinations of different chords. That is, if we say that is the force, the strong nuclear force is operational between the protons. So you know that what we mean by the proton. The proton is basically the combination of 2 up cards and 1 down card. So the diagram will look like this, and in between these 2 protons, if we say that we have 2 protons, and between these protons we say that a strong nuclear force. So the strong nuclear force will be exerted due to the exchange of the gluon. Here you can see that the resistor-like signs. These resistor-like sign with the small g is basically for the gluon. That is, the particles, I mean the quarks, they are continuously exchanging the gluons. So if we say that, I mean, the same concept apply for the neutrons. I mean, we say that the neutrons, they can exchange the gluon as well. But we remember neutrons, they are being a combination of 2 down cards and 1 up card. So what about the weak nuclear force? So if we say that, uh, just like you know about the concept of the weak nuclear force, the weak nuclear force is basically responsible for the radioactivity. So if you want to study about the weak interactions or weak nuclear force, so you should know about the uncertainty principle, that is uh, delta T, delta E is greater or equal to H by 2 pi, which we call the most famous uncertainty principle. So you know there's been interactions between the cars, uh, and that interaction is being governed by the gluon. So when they are interacting, so as a result of that interacting, we have charge boson, just like you can see it here. W negative means it's been the charged gluon. So when the down cars they are being interacting, so as a result of that interactions, we have the charge boson. Uh, Here you can see it here in this particular diagram, and you know that as a result of that interactions, we have beta decay, and as a result of that beta decay, we have protons. Along with that, we have electrons and uh, an electron and neutrino. So let me repeat it again. Uh, Initially, we have a neutrons, just like you can see it here in this particular diagram. Neutron is being composed from two down cars and one up cars, just like you can see it here. On the left hand side, we have neutrons, and similarly on the right hand side, we have a neutrons. I mean, the constituents are being the same, the two down cars and one up cars, and in between them, there's been interactions with the exchange of the gluons. So what we say that if this exchange continue, and we say that if weak interactions, if there is weak interactions between the neutrons, so as a result of that weak interaction, what actually happens? So here you can see that when weak interactions occur, so as a result of that weak interactions, we have electrons, and along with that we have a neutrino. And what actually happened as a result of the weak interactions, neutrons is being converted into a proton, and the overall process is the beta decay. And this particular beta decay, a neutron is converted into a protons, uh, and along with that we have electrons and neutrino. So how do forces merge or freeze out? I mean, it's the questions, just like we have the idea, and we're saying that the people have got a Nobel Prize for the unification of the forces. So how to answer the force that, how to answer the questions, and how do forces merge or freeze out? For example, electro-weak force. So here you can say, you can have a clear look on the diagram. I mean, on the left hand side, we have the diagram for the electromagnetic force. Here you can see that how electron and electron interact, and how the interactions results uh, into an electromagnetic force. So along with that, you can have a close view on the weak nuclear interaction. That is, we have the interactions among the electrons. Uh, the upward electron and downward electrons, and we say that this interactions is governed by the neutral boson. Here you say that, I mean, it's an electromagnetic force. The interaction between the electron is we have photons. Photon is also bosons. But if we from the electromagnetism or from electromagnetic force we come to weak nuclear interactions, so we say that the interaction is basically governed by the neutrals boson. So what actually happened, or how these two interactions they are being unified, and electro-weak unification. So its energy is very greater than 100 giga electron volt. Uh, the Z, or we said the neutral bosons and protons can be equally produced. I mean, this was the key idea for electro-weak unification. And what is that? Is that if we increase the energy, we have the interactions, and for these interactions, if we increase the energy, how much we increase the energy? We increase the energy much more than 100 giga electron volt. So if we have this much of energy, so at this energy, uh, the scientists they're saying that uh, the neutral bosons and photons can be equally produced. What it mean? It means that the two forces act the same. At this particular energy, we're saying that the neutral bosons and photons can equally be produced. So what it means? It means that the two forces act the same. So that's why these two forces they are being unified into a single force, which has been given the name of electro-weak unifications. And the basic concept was, these two forces that they are acting the same. Its energy greater than 100 giga electron volts. So similarly, we have annihilations and creations. If you look upon the annihilation process, that is, we have electron and positron. They annihilate through the emission of gamma rays. Uh, Similarly, we can say that we have a gamma rays, high energetic gamma rays photons, and these photons, when they've been passing through a high energy nucleus and a nuclear field, high energy nuclear field, so they are being disintegrated into electron and positron pair, or it's been uh, disintegrate, or it's been results into the creations of negative and positive muons. So that should be able to produce muons and uh, positive and negative muons and electrons, positrons, annihilation. So this is the key phenomena. This is the similarity. We can look upon the inhalations, so the way the inhalations occurs. So similarly, so with that particular energy, as we mentioned on the previous slide, the same way we can create the electron positron pair. By the similar way, we can create the muon pair. That is the muon negative and positive muon pair. That's how that these forces they are being unified. Here you can see it here. We have electron positron pair, and these electron positron pairs, when they've been inhalated into gamma rays photons, so these gamma rays photons again they can generate what they can generate the muons, that is muon negative and muon positive pair. Or we can say that we have the electrons, so electron positron pair, and these electron positron pairs, when they do have the interaction, first they annihilate into gamma rays, and after the annihilations they move toward the creations, and as a result of that creation they produce the charge, that is the positively charged particles and negatively charged particle. So this is the key idea for the annihilation. This is the key idea for the unification of the forces, that when we are saying that these two forces they behave in the same manner, or they are actually the same forces. So first of all, we need to give the reasons, we need to give the example, we need to give the experimental verifications, that how and under what conditions these forces they can be called the same force, or they can be considered as a unification. So these are some of the example of how the forces they are being unified. And this is the standard models of the elementary particles. That is, we have the unifications of the quarks. We have classified the particles according to their characteristic and different generations. And we're saying that according to the characteristic of the particles, we have classified them into first, second, and third generations. This all for this lectures. In the coming lectures, we will talk in more details about different type of the particles, their classifications, and also about their different generations. And we will discuss that what actually the generation means, and why they are being divided into different generations, and what is the generation which is being responsible for the creations of the universe, and what are the other generations responsible for. So tell then, bye bye.